Hello students. In this module, we will learn a very important topic from ionic equilibrium. At first, we need to understand the word equilibrium in terms of chemistry. In chemistry, it is always a dynamic equilibrium. You can understand it better if we consider a tank where the inflow is equal to the outflow. As both are equal, there is no net change in the water level in the tank. But this is not considered a static equilibrium, as there are changes that are happening in this system. In this module, we will learn about an equilibrium like this but involving ions. Hence, it is called ionic equilibrium. One of the symbols which we will often use in the ionic equilibrium is a double-headed half arrow. This is the representation of equilibrium, symbolizing that both forward direction reactions and backward direction reactions are happening in that chemical reaction. So this is seen only for a reversible reaction. The first thing which we need to know in the ionic equilibrium is electrolytes. An electrolyte is a substance that dissociates in water into charged particles called ions. Positively charged ions are called cations. Negatively charged ions are called anions. Simply, an electrolyte is a substance that can conduct an electric current when melted or dissolved in water. Now, based on their ability to dissociate, electrolytes are divided into two types, strong and weak electrolytes. Strong electrolytes dissociate completely into their corresponding ions. Why? Weak electrolyte dissociates feebly. No conductivity is shown by the non-electrolytes. Now, if we see the water, it is a weak electrolyte. Thus, it will dissociate very less, forming H+ and OH-, as the H+ being unstable, reacts with a nearby water molecule and forms a hydronium ion. Now we are clear that the water dissociates into hydronium ion and hydroxide ion. Before going any further, let us see the general way of representation of an equilibrium constant. For a general equation, AA plus BB reversibly gives CC plus DD. The equilibrium constant K will be written as square bracket C power C into square bracket D power D divided by square bracket A raised to the power A into square bracket B raised to the power B. Here the square bracket represents the concentration of that component, which is usually the molarity of that substance. Let us see how to derive the equilibrium constant of ionization of water. Similarly, for ionization of water, it can be written as the concentration of hydronium ion into the concentration of hydroxide ion divided by the concentration of water raised to power 2. The concentration of H2O is transferred from the denominator to the other side, as water is a pure liquid, and its concentration remains constant. When this value joins with the equilibrium constant, it gives a new constant, Kw, which is called the ionic product of water, or autoprotolysis constant. The value of which changes with the temperature proportionally. Kw value at 25 degrees Celsius is 1 into 10 to the power minus 14 moles per liter square. If the temperature increases from this point, the value will increase and will decrease on decreasing the temperature. So, if we see the graph between Kw versus T, it will be a straight line. Deionized water is neutral. Thus, the concentration of hydronium ion and hydroxide ion in it will be equal. At 25 degrees Celsius, it will be 1 into 10 to the power minus 14 divided by 2, which will be 1 into 10 to the power minus 7. After discussing the ionic product of water, let us learn the pH scale. Sorensen, 1909, introduced the term pH scale to determine the concentration of hydronium ions or H+ ions in the solution. The pH of a solution is the negative logarithm to the base 10 of the concentration of hydronium ion. The scale of pH starts from 0 to pKw, where pKw is equal to minus log to the base 10 kW. Also, the neutral pH is pKw by 2. Thus, the upper limit of pH and neutral pH both depend on the ionic product of water. Hence, at 25 degrees Celsius, pKw is minus log to the base 10 of 10 to the power minus 14. This, minus 14, when taken to the other side of log, it becomes 14, and value of log 10 is 1, which means that the pKw at 25 degrees Celsius is 14. Hence, the pH scale will be from 0 to 14, while neutral pH will be 7. pH value, which is less than 7, at this temperature is acidic, and as the value of pH decreases, the acidic strength increases. While if it is greater than 7, then it is basic in nature, and the strength of the base increases as the value of pH increases. Now, let us see the properties of pH scale. pH scale range is always temperature dependent. As temperature increases, both the upper limit of pH and neutral pH value decreases, while the reverse can be said when the temperature decreases. pH scale is very convenient, as the value is made simple by taking the negative log of the concentration of hydronium ion. Even though the pH range seems small, it covers a wide range of hydronium ion concentrations. The next thing to discuss in this module is the limitation of pH scale. First one is, it can't account for the relative strengths of acids and bases, especially when the pH value is the same. It is not applicable for a concentrated solution. As for acid, the value will come in negative, while for the base, it will come more than 14 at 25 degrees Celsius. Thus, we can say that the range is not absolute at a given temperature. Finally, uses of pH are in brewing for salt quality check, for milk quality analysis, in soap industry, as well as in the medical field. Let us summarize. In this module, we learned about the ionic product of water, which is a concentration of hydronium ion multiplied by the concentration of hydroxide ion. Next is pH, which is the negative logarithm to the base 10 of the concentration of hydronium ion. The pH scale will be from 0 to 14, while neutral pH will be 7. pH value, which is less than 7 at this temperature, is acidic, while if it is greater than 7, then it is basic. Next is the properties of pH scale. pH scale range is always temperature dependent. pH scale is very convenient. It covers a wide range of hydronium ion concentrations.